Power. It's what drives our machinery, our industry, our economies, and our livelihoods. And more often than not, that power is extracted from petroleum-based products. For many years, scientists, engineers, and researchers have been searching for alternative methods of generating that power. But while the rest of the world has been trying to change the fuel sources we use, one visionary company has focused on changing the way we use both gasoline and other fuels with much greater effectiveness and efficiency. Duke Engines, a technology development company based in Auckland, New Zealand, have spent the last 10 years completely rethinking the concept of the internal combustion engine, and have made breakthroughs in engine design that have achieved a complete step change in internal combustion technology. The basic internal combustion engine has not changed over the more than 100 years of its development. Designers have focused on the fuel delivery, gas exchange, and combustion systems, the fuel that's used, the way the fuel is mixed, delivered, and compressed, the way the ignition is timed for maximum power. In that search for power, they've used an ever-increasing amount of smart technology, computer monitoring and control, intelligent feedback systems, and ever more complex timing and valve train assemblies. Duke Engines have changed the configuration of the engine itself, completely changing how the engine physically works and how power is transmitted to the flywheel with remarkable results. Duke Technology has focused on the fundamental arrangement of cylinders and porting, creating a smaller, lighter, smoother running, almost vibration-free power plant with no power loss through the usual cam and valve arrangement. A standard internal combustion engine works when a fuel charge is ignited under pressure, pushing a piston down a cylinder where its linear motion is converted via conrod into rotational motion of a heavy crankshaft held in an even heavier block. To increase power, numbers of cylinders are repeated in rows, either inline or in a V configuration, introducing even more weight and complexity. The Duke engine reforms this linear arrangement into a circle, creating a true axial engine. The standard piston cylinder sets are mounted in a single cast and machined monoblock, revolving slowly around and in line with the crankshaft. The pistons drive a star-shaped element called a reciprocator, allowing all moving parts to operate in a purely sinusoidal or wave-like motion. The reciprocator, in turn, drives a central crankshaft in the opposite direction, a key to many of the Duke engine's advantages. Instead of the usual complicated poppet valve system, the cylinders themselves slide past ports and spark plugs that are mounted in the stationary head ring. As the cylinder slides past the inlet port, the fuel and air charge is let in. The charge is then compressed before the cylinder is exposed to the spark plug. The charge burns, driving the piston down in a power stroke. The piston then rises again, ejecting the combustion gases through the exhaust port to complete the four-stroke cycle. With just 5 cylinders requiring only 3 spark plugs and 3 fuel injectors, the engine has as many power strokes per revolution as a conventional 6-cylinder engine, but with at least a 30% weight saving and an astounding reduction in the number of parts. Originally conceived and developed by Duke founder Noel Duke, Duke Engines has put together an international team to help develop the concept, including experienced engineers previously at Cosworth Technology, now Mahler Powertrain in the UK, and other major engineering companies, forming a highly skilled CAD design, analysis and development team. From an initial proof of concept, the Duke team have now developed their 3rd generation design. A rigorous test program conducted at Mahler Powertrain has proved the engine's capability and its exciting potential. Even at this prototype stage, key performance characteristics have matched those delivered by conventional production engines. Recent breakthroughs, now the subject of patent applications, pave the way for Duke to approach engine speeds not previously achieved in axial engines. Potential applications of this axial technology go beyond just the Duke engine, opening up further opportunities for this evolving technology. Duke's developing engine technology enjoys a number of fundamental advantages over conventional four-stroke internal combustion engines. Its compact combustion chamber has no hot exhaust valves present and is remarkably resistant to pre-ignition of the fuel-air mix. It can utilize a higher compression ratio, delivering greater power for a given amount of fuel. Spark ignition Duke engines have run compression ratios as high as 14:1 on 91 octane fuel without detonation, delivering a large improvement in efficiency that leads to lower fuel consumption and hence lower overall greenhouse emissions. The Duke concept has a size and weight advantage, producing a far more compact package than is possible with conventional engines. It simply takes up much less space. A smaller engine allows savings throughout the supply chain, reducing handling and storage costs. Savings are even greater with larger capacity engines. The Duke's size advantage increases as engine capacity is increased. This compactness gives designers great flexibility. For example, where current automotive engines struggle to meet new vehicle pedestrian impact rules, the Duke engine's low height readily provides the bonnet clearances needed. The design weighs significantly less, with current unoptimized prototype models weighing about 2/3 of modern equivalents. It provides unmatched power density potential, allowing weight savings throughout the structure of a vehicle with cost savings to manufacturers and end users alike. So what does this mean for real-world applications? A smaller, lighter, less complex engine with equivalent power to existing larger engines opens the way for design engineers to completely rethink the powertrain in their application. In nearly every type of vehicle or transport application, the power unit represents a significant negative weight and space element. Take the typical outboard marine engine. Using Duke engine technology, the motor can be lighter, with no vibration, and significantly fewer parts. Set upright, the entire fuel, ignition, and engine management system can be easily accessed from the top of the engine. There is no power loss through the usual cam and valve arrangement. The result is a smaller, tighter, more convenient unit, delivering full power characteristics with virtually no vibration. Another application is for the manned and unmanned light aircraft and military drone market. Properly developed, the Duke engine technology can bring significant weight and space savings with resultant increase in range and a reduced maintenance regime. The latest iteration of the Duke engine has seen the successful testing of alternative fuel sources beyond ordinary gasoline. Duke engines can run on kerosene, avgas, or green fuel such as ethanol. The Duke engine concept has the capability to bridge the gap between traditional and alternative fuel engine technology. Because of its size and weight savings, its power density and refinement, the Duke is perfectly positioned to enter the hybrid vehicle engine market in range extender applications. And the Duke engine's suitability for military applications is obvious. A smaller, lighter engine, delivering the same or greater power while increasing range and payload capabilities and allowing for multi-fuel running, makes it the perfect engine of choice for light and medium land, marine and air applications. Duke engine's advances in internal combustion technology represent nothing less than a step change in the evolution of the world's largest source of motive power. The Duke engine features a design that has far smaller packaging than today's conventional engines. One that is significantly lighter than its conventional cousins. Higher compression ratios that promote superior efficiency. Low vibration with near perfect mechanical balance. Breakthroughs in multi-fuel and variable compression technologies. An engine that will free designers to challenge convention. With proven concepts and third-generation prototype built and in test, Duke Engines is looking right now for partners to join in developing this visionary technology around application-specific parameters. We invite you now to get on board and take the next step with Duke.